welcome back. In the last lecture, we have derived the Fourier inversion theorem for a Schwarz class function. Just to recall, Fourier inversion if f is in Schwarz space, then we have proved f of x, this is equal to minus infinity to infinity f hat xi e to the power 2 pi I xi x dxi. This is what we had proved, and now we were asking the another important theorem, that is the Plancherel theorem. What will be the statement of this? So, again you recall we have defined f in Schwarz space. We denoted that the norm of f is equal to minus infinity to infinity mod of f of x square dx whole to the power 1 over 2. So, then the Plancherel theorem if f is in Schwarz space, then we know that f hat is also in the Schwarz space, and then we get norm of f square which is nothing but, or rather we can just put it minus infinity to infinity okay. So, now we have here the mod of f of x square, and on the right hand side we have mod of f hat of xi square. Now, the trick is that how do I convert this into some Fourier transform of some function g hat? Can we find a g such that g hat equal to mod of f hat of xi square? Then if that is the case, this will imply that by Fourier inversion theorem, if g is in Schwarz space, if we can manage to find such a g, then this will be g of 0. So, let for f in Schwarz space define f tilde of x, this is equal to f of minus of x bar. Now, let us compute f tilde. Clearly, if f is in the Schwarz space, then f tilde is also in the Schwarz space. So, we talk of f tilde hat at xi, this is and by putting the definition, and this is equal to, if I make a change of variable, then this is x going to minus of x, then this is minus infinity to infinity f of x bar e to the power 2 pi I xi x dx. If I take the bar outside the integral, then this is minus 2 pi I xi x dx whole bar and this quantity is nothing but f hat of xi whole bar. So, this f tilde hat is equal to f hat conjugate. Now, let us take, we know that then f convolution of f tilde, because both of them are in Schwarz space. So, this is in the Schwarz space. If I take this hat of xi, then we know that this is f hat of xi, and then this is f tilde hat of xi. So, this is equal to f hat of xi and f hat of xi bar, which is nothing but mod of f hat of xi square. So, successfully we have got uh, a function g in the Schwarz space, namely f convolution of f tilde, whose Fourier transform is f hat of xi mod square. Therefore, what we get is that minus infinity to infinity mod of f hat of xi square d xi, this is equal to minus infinity to infinity f convolution of f tilde hat at xi d xi. Because this is f convolution of f tilde is in the Schwarz space. So, what we get by the Fourier inversion, we get that this is f convolution of f tilde at 0 by inversion, and this by definition is going to be minus infinity to infinity f of x, then f tilde of minus of x dx. This is the definition of convolution, which is equal to minus infinity to infinity f of x, f tilde of is f of minus of x, here it is minus x. So, this is f x bar dx, and which is nothing but our required quantity, that is mod of f of x square, and this proves the Plancherel formula. Okay, so, now we have the inversion, we have the Plancherel. So, our analogy with the series as well as with the finite group. So, we have proved two fundamental result of Fourier analysis, restricting ourselves to the Schwarz space. So, now it is a natural question is that how I am going to relate this Fourier transform with the Fourier series, and also like one can think this as a practical problem in many of the engineering. In the we get the frequency of certain functions only at the discrete point. So, we have discrete data. So, now with this discrete data, how we are going to reconstruct our function, the original function which is defined on R. So, can that be possible? So, let us try to concretize this vague statement, and let us let f in Schwarz space. It has very good decay. So, therefore, if we define f sharp of x, this is equal to summation over n varies over z f of x plus n. Then this infinite sum, this exists because you can always say that mod of f of x plus n, this is lesser equal to some constant by 1 plus mod x plus n square. So, because it is in Schwarz space, therefore, this exists, and not only that, this f sharp is one periodic, that is f sharp of x plus 1, this is equal to summation over n varies over z f of x plus 1 plus n, which is again by substitution we will get that this is f of x plus n, which is equal to f sharp at x. So, this shows that this is a one periodic function, and now if we look at 0 to 1 f sharp of x dx, this is I can put the mod here, then this is lesser equal to summation over n 0 to 1 mod of f of x plus n dx by making a change of variable. This is n varies over z, this is n to n plus 1 mod of f of x dx. So, now this is equal to minus infinity to infinity mod of f of x dx. So, if f is positive, then we get the equality, and which is finite, f is in the Schwarz space. So, now f sharp is as a periodic function is also integrable. Therefore, we can talk about the Fourier coefficient of f sharp, because when I am looking at it in 0 1. So, this is going to sit in the integer. So, now f sharp hat at n we can define to be 0 to 1 f sharp of x e to the power minus 2 pi I x n dx as the Fourier coefficient of a one periodic function. Now, this is equal to integral 0 to 1, this is summation over m varies over z, we will write f of x plus m e to the power minus 2 pi I x n dx. Now, again change this is all this in the Schwarz space. So, I can justify changing the sum as well as the integral. So, if I take this out, then now I make a change of variable. So, if I do x plus m to x, then this is going to m to m plus 1, and then e to the power minus 2 pi I x is x minus of m and n dx. Now, this is equal to summation m varies over z integral m to m plus 1 f of x, then e to the power minus 2 pi I n x, because e to the power 2 pi I m n, that is going to be equal to 1. So, this is nothing but f, because this sum m to m plus 1 will be the integral over minus infinity to infinity. So, minus infinity to infinity f of x e to the power minus 2 pi I n x dx, which is nothing but f hat of n. So, here this periodization of f what we are taking. So, that we can think of it as a one periodic function, can do the Fourier series there, and there the Fourier coefficient is nothing but the Fourier coefficient of f at in all those integer. So, now it is f sharp is a nice function. So, what we can define by the inversion formula for Fourier series tells us that this f sharp of x, this is equal to summation n varies over z minus infinity to infinity f sharp hat at n e to the power 2 pi I x n, and this is nothing but, so this will imply f sharp is what? Summation over x n varies over z f of x plus n, which is equal to n varies over z. F sharp hat at n is f hat of n e to the power 2 pi I x n. So, this is called the Poisson summation formula. Which is extremely useful not only in the mathematics in the field of number theory, as well as in signal processing and various other science. Okay. So, now in particular, if x is equal to 0, if x is equal to 0, then this formula will look at f of n is equal to summation over n varies over z f hat of n. This is when x is equal to 0. So, f hat of n sum over to f of n. So, let us see some application of this Poisson summation formula what we have derived. Okay. So, now for example, let a greater than 0, then we would, it says that n is equal to minus infinity to infinity e to the power minus a square n square. This is equal to square root of pi by a summation n from minus infinity to infinity e to the power minus pi square n square by a square. Okay. So, now let f of x is equal to e to the power minus a square x square. Now, this what we can see is that f from this we know that summation over f n, n this is equal to summation over n varies over z f hat of n, Poisson summation formula. Now, this is equal to the left hand side, summation over n f of n is nothing but the left hand side quantity. So, now what essentially we need to find is that the f hat of n. F hat of n. So, now let us look at, let g of x is equal to e to the power minus pi x square. We know that g hat of xi, we have computed this is equal to minus pi xi square. Now, f of x, I can write this as e to the power minus pi, then a square x square by pi. This is what. So, now this is equal to g of a x by root pi. Now, this is the dilation of the Gaussian. So, now when we are writing g hat of n, then this is going to be 1 over a by square root of pi, and then e to the power minus pi xi square, means n square is n square divided by a square by pi. So, this is equal to square root of pi, because we know that if f of delta is defined to be f of delta x, then f delta hat at xi, this is equal to 1 by delta f hat of xi by delta. Now, if this is e to the power minus pi square n square by a square, and that is what we wanted to prove. Okay. And similarly, now what one can, another number theory application is that to find the value of n from minus infinity to infinity 1 by n square plus a square. Okay. So, now obviously, this is if we define f of x is equal to 1 by a square plus x square, it is no more a Schwarzschild function, but it has a good moderate decay. So, we can actually ensure that, look at the Poisson summation formula what we are using over here. So, we are using that the sum is well defined, this sum is well defined, and it is in obviously one periodic function, and this is a integrable, then we are computing the Fourier coefficient. So, obviously, even if we do not have the Schwarz space, we have a decay like this, then we are going to run through the proof as it is. So, this what we can have the Poisson summation formula. Now, it is well known. So, you grant me that if f is this, then f hat of n, or we can do it for xi too, but yeah, what we need is f hat of n. Then the f hat of n is equal to, can be computed, pi by a e to the power minus 2 pi a mod of n. So, this can be easily computed by residue calculus, but it is given, or you can assume this to be true. Now, once you can compute this f hat of n, then by the Poisson summation formula what you get is n equal to minus infinity to infinity 1 by n square plus a square, that is f of n, which definitely is going to be n minus infinity to infinity f hat of n. This is the Poisson summation formula, and which by definition is pi by a summation over n from minus infinity to infinity e to the power minus 2 pi a mod of n. So, now this certainly if we write this first, if we take out the 0 part, then we have got pi of a this is 1 plus summation n from 1 to infinity 1 to infinity. In the positive side it will be minus 2 pi a n, and in the negative side minus infinity to minus 1 e to the power 2 pi a n. Now, you change n going to minus of n, then you will get n equal to 1 to infinity e to the power 2 pi I 2 pi a n. So, this will be twice of this. So, then that is easy. Now, this is equal to pi of a into 1 plus, this is a geometric series. If I am taking minus 2 pi a, if I take it out, then this 1 minus e to the power minus 2 pi a. So, this is pi by a 1 minus e to the power minus 2 pi a, and then plus 2 times e to the power minus 2 pi a, this is 1 plus e to the power minus 2 pi a. This is a well known formula. So, what we know is that this is pi by a cot hyperbolic pi by a. So, if we know the formula n from 1 to infinity 1 over n square is pi square by 6. Now, this is what is going to happen, that if I shift it by n square plus a square, I am going to get that this is pi a uh, uh, times cot hyperbolic pi by a. Okay, so we will see some more application of the Poisson summation formula in the next lecture. Thank you.